Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into Apache REEF, a powerful runtime environment designed for scalable machine learning and big data processing. Originally developed by Microsoft Research, REEF bridges the gap between high-level application logic and low-level resource management. It supports both batch and iterative computing models, making it ideal for complex machine learning algorithms. REEF integrates seamlessly with popular resource managers like Yarn and Mesos, offering flexibility in deployment. Before REEF, developers had to manually manage communication between machine learning frameworks and cluster resource managers. This often led to boilerplate code and reduced flexibility. REEF was built to abstract these complexities, allowing developers to focus on algorithm design rather than infrastructure. It supports custom logic for scheduling, fault tolerance, and event handling, making it ideal for high-performance iterative algorithms used in machine learning. REEF introduces several core concepts to manage distributed computation. The Evaluator is a container that runs on a cluster node and executes user-defined tasks. Each task is wrapped in a context, which provides the runtime environment. The driver is the central coordinator that manages evaluators, tasks, and handles events throughout the execution lifecycle. Understanding these components is crucial for mastering REEF. The architecture of Apache REEF is built around a central driver that coordinates the entire system. Evaluators are launched on cluster nodes to execute tasks provided by the user. Each task runs within a context, which manages its lifecycle and environment. This modular design allows for flexible and scalable execution of complex algorithms. REEF's event-driven model allows developers to define custom behavior for various lifecycle events. Tasks and drivers can register handlers for events like start, stop, and fail. This enables fine-grained control over execution, supporting asynchronous and reactive programming patterns. It's a powerful feature that enhances flexibility in distributed computing. Apache REEF abstracts resource management complexities by integrating with systems like Yarn and Mesos. It supports dynamic allocation and deallocation of cluster resources, making it efficient for iterative algorithms that require persistent state. This integration ensures optimal resource utilization and simplifies deployment in containerized environments. Fault tolerance is a critical aspect of any distributed system. REEF provides automatic recovery mechanisms for failed evaluators and supports checkpointing to persist state. It detects failures through event handlers and integrates with cluster-level fault tolerance mechanisms, ensuring robust and resilient execution of tasks. Programming in REEF involves defining tasks with custom logic, wrapping them in contexts, and registering event handlers in both the driver and task components. Jobs are submitted using REEF's client APIs, which handle communication with the cluster resource manager. This model offers high flexibility and control over distributed execution. The lifecycle of a task in REEF begins with submission from the driver. An evaluator is then allocated, and a context is initialized to wrap the task. The task logic executes within this environment. Upon completion or failure, appropriate handlers are triggered to manage the outcome. The driver in REEF goes through several lifecycle events. It starts by initializing and requesting resources from the cluster manager. Once evaluators are allocated, tasks are submitted for execution. The driver transitions to completed if all tasks finish successfully, or to failed if an error occurs. These events can be intercepted and handled programmatically. Evaluators in REEF are lightweight containers that run on cluster nodes. They are allocated dynamically based on resource requests made by the driver. These containers support various resource types including CPU, memory, and even GPU. Once a task completes, evaluators can be reused for new tasks or discarded to free up resources. Contexts in REEF provide the execution environment for tasks. They can be structured hierarchically, allowing for modular design and code reuse. Contexts also enable sharing of state between tasks, which is particularly useful in iterative algorithms where intermediate results need to persist across iterations. Event handlers in REEF allow developers to inject custom logic at various stages of execution. Handlers can be defined for evaluator lifecycle events such as start, stop, and fail. Similarly, task-level handlers manage execution stages. This enables reactive and asynchronous programming, giving developers fine-grained control over system behavior. The REEF client APIs provide a simple interface for submitting jobs to the REEF runtime. Users can monitor job status, retrieve results, and access logs through these APIs. They support both Java and Net, making REEF accessible to a wider audience of developers. When integrated with Yarn, REEF acts as the application master. It requests containers for evaluators and manages their lifecycle. REEF also handles fault tolerance and optimizes resource usage, making it a powerful framework for running machine learning workloads on Yarn. REEF integrates with Apache Mesos by using its offer-based resource allocation model. It supports both fine-grained and coarse-grained execution modes. REEF registers as a framework with Mesos and handles task launching, ensuring compatibility with the broader Mesos ecosystem. Performance in REEF is optimized for iterative tasks that require persistent state. It features low-latency event handling and communication, supports in-memory computing, and is optimized for cloud-scale deployments. These features make it suitable for high-performance machine learning applications. While Apache Spark is known for its broad ecosystem and SQL support, REEF is specifically designed for machine learning and iterative computing. REEF offers lower-level control over execution, which can be advantageous for custom algorithms. However, Spark benefits from a larger community and more extensive documentation. One of the most notable real-world applications of REEF is Microsoft's project Brainwave. This platform provides real-time AI inference using FPGA-based accelerators. REEF manages the lifecycle of these accelerators, enabling low-latency and high-throughput inference. It's deployed in Azure to power cloud-scale AI services. In scientific computing, REEF is used for dynamic resource allocation in simulations and long-running experiments. Its fault tolerance mechanisms ensure reliability, and it integrates well with both HPC clusters and cloud environments. Custom event handlers allow precise control over experimental workflows. To get started with REEF, you'll need to install Java and Maven. You can download pre-built binaries or build REEF from source. Next, configure your local runtime environment and run sample applications to verify that everything is set up correctly. This is a great way to begin exploring REEF's capabilities. Writing your first REEF application involves defining a simple task with custom logic, creating a driver to manage it, and registering event handlers for lifecycle events. Finally, you submit the application using the REEF client. This basic example helps you understand the core components and workflow. Checkpointing in REEF allows you to save and restore application state, enabling fault tolerance for long-running jobs. It supports both local and distributed storage options, including integration with HDFS and cloud storage systems. This feature is essential for robust and scalable applications. Hierarchical contexts in REEF enable modular and reusable task designs. They allow sharing of state between tasks and support complex execution workflows. This improves code organization and maintainability, especially in large-scale applications with multiple interacting components. REEF's flexibility extends to custom resource managers. You can integrate with proprietary or custom clusters, define custom allocation and scheduling logic, and support specialized hardware like GPUs or FPGAs. This enables hybrid cloud and on-prem deployments tailored to specific requirements. Monitoring and debugging in REEF is facilitated through logs and metrics accessible via the REEF client. You can use event handlers for custom monitoring logic and integrate with external tools. Debugging tasks and drivers is supported both locally and in a cluster environment, ensuring smooth development and troubleshooting. Security in REEF includes support for secure communication channels and integration with cluster-level security frameworks. It offers role-based access control for tasks and supports data encryption for sensitive workflows. These features ensure that your distributed applications remain secure and compliant. Apache REEF is actively developed by Microsoft Research and integrates well with Azure and other Microsoft services. It has a growing open source community, with documentation and sample projects available to help you get started. This ecosystem ensures ongoing support and innovation. The future of Apache REEF lies in its focus on machine learning and AI workloads. Enhanced support for Kubernetes, improved integration with cloud-native tools, and expansion of language bindings are on the roadmap. These developments will keep REEF relevant in the evolving landscape of distributed computing. Apache REEF is ideal when you're building custom machine learning algorithms that require fine-grained control over execution. It excels in iterative and long-running distributed tasks and integrates seamlessly with Yarn or Mesos clusters. If these use cases match your needs, REEF is a powerful choice. REEF may not be the best choice for simple batch processing, where Apache Spark would be more suitable. It requires experience in distributed systems, isn't optimized for SQL-based analytics, and works best in environments with Yarn or Mesos. Consider these factors when evaluating REEF for your project. To dive deeper into Apache REEF, explore the official documentation, sample projects on GitHub, and research papers from Microsoft. Community forums and mailing lists are also valuable resources for learning and troubleshooting. These materials will help you master REEF and apply it effectively. Let's walk through a sample REEF application. First, define a task with custom computation logic. Then, create a driver with event handlers to manage lifecycle events. Submit the job using the REEF client API and monitor execution to retrieve results. This example illustrates the core workflow in action. To optimize performance in REEF, start by tuning Evaluator resource requests to match your workload. Use checkpointing for fault tolerance, minimize communication overhead, and profile your event handler logic. These practices will help you achieve efficient and scalable execution. Common pitfalls in REEF include overcomplicating context hierarchies, neglecting event handler registration, ignoring resource limits, and skipping local testing. Avoid these by keeping designs modular, registering all handlers, respecting cluster quotas, and testing locally first. In summary, Apache REEF bridges the gap between machine learning frameworks and resource managers. Its event-driven model offers fine-grained control, making it ideal for iterative and custom ML algorithms. It integrates seamlessly with Yarn, Mesos, and cloud platforms, ensuring flexibility and scalability. Thanks for watching this deep dive into Apache REEF. If you found it helpful, don't forget to like, subscribe, and leave your questions in the comments. Explore more tutorials on distributed computing, join the REEF community, and stay tuned for upcoming content. See you next time. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.